Welcome back to the stream. Anybody tuning in early? Another chill embedded systems, firmware, hacking around, debugging stuff, that kind of stream. There's Tuco already. Hey, Tuke. What do you want, Tuke? Oh, good morning. Mike says good morning from New Zealand. Oh, that's wonderful. Seems like a pretty nice place to visit sometime. Oh, Tuco, don't bite the camera cable. Alright. It's a little out of focus. Anyway, welcome back to the stream. So, just previously, we had been working on the firmware for one of the robots in the little constellation of microcontrollers that's going to be making up this cat-following camera robot. I had been working on the microcontroller that had just like a bunch of random sensors attached to it, mostly because I wanted to make sure all those sensors were going to work out before getting too deep into the CAD design. So now that robot actually has a pretty complete kit of firmware and electronics. It just needs mechanical design at this point. I can show you the pieces I've got at this point. Got the gimbal and microcontroller and a bunch of sensors. Badly in need of an enclosure at the moment, so I'm designing that. Tuco is giving me no peace. Tuco, what do you want, little guy? got that little guy. You let it escape. I wonder if that'll hold his attention for a little while. All right. So over here back on the desk, we have another one of those TI TM4C129 whatever dev boards that we've been using. These are mostly handy because it's a pretty fast ARM Cortex M4F processor with built-in 100 base T Ethernet and a bunch of handy peripherals. So I think it's got 8 timers, each of which you can actually use as 2 timers plus a couple of others. So it's actually got like 18 timers or something in total, and tons of interrupts and serial ports and A to D converters, and so it's a really nice little platform to build a kind of sensor acquisition or motor control device around. So that's pretty much exactly what this project has been. And then over here, this is part of the winch robot so far. It's the actual spool here attached to, oh, that was a big jump. She could have just jumped all the way up onto the rack. So 24-volt drive motor, spool, and then some rollers back in there. And then as far as the electronics is concerned, the relevant parts here, besides the motor, are an optical encoder and a strain gauge here, which measures the force actually on this, this cord. So we'll get to this soon. I want to actually hook this up to the microcontroller so we can test the mechanical design so far and see how bad it is. Actually, mostly I want to try programming this to run the cord in and out a whole bunch to make sure that it doesn't tangle. But it seems like, instead of building something special just to do that, I might as well actually just implement enough of the motor control that I can get it to do that using the code that I actually intend to use. So that's kind of the track I'm on right now. So to get this to work, the main sensors we're dealing with, well, really the only sensors in this particular robot are the quadrature encoder and the strain gauge. So the quadrature encoder, we're actually using a built-in quadrature encoder peripheral on the microcontroller here. So they've actually got a peripheral where you can just give it the 2 phases of a quadrature, so like the 2 out-of-phase square waves that move as your actual rotating encoder moves. So it'll actually measure, it'll count those edges and use that to determine speed. It can also automatically, keep track of position by figuring out speed and direction. It can also calculate velocity, which I think it does by timing the pulses. I forget exactly how the velocity part works. We might have to go look at that documentation again. But yeah, so it's got a nice quadrature encoder peripheral that that can give us a nice position and velocity representation just right out of the signal we get from this encoder device. So we'll take a look at that. I've got a driver kind of hacked together for that should at least let us see what's going on there. We'll see how correct that is. The force feedback is a little more complicated. So for force, I'm using this mechanism, which I've got another copy of here. So here, this section of the strain gauge would be fixed to the immovable part of the robot, and then the cord goes out through this pulley. And so as the cord pulls in the direction of this arrow, it exerts force on this bar, which actually slightly compresses this half and slightly stretches this half. And so that very slightly changes the resistance of little foil patches that are glued onto the metal. So this is the same sensor you'd see inside of just like a kitchen scale or any kind of small weigh scale that goes up to 5 kilograms. So I'm using the same sensor, so this is actually also a chip that you would find in a scale like that. So it's actually a single chip solution that has the amplifier, a 24-bit A to D converter, and a really simple kind of SPI compatible serial interface. Oh, it goes back on the rack. Alright, so this chip is called the HX711. Is this thing made by Avia Semiconductor. Specifically says it's for weigh scales. So we're using it slightly off-label, but, you know, I think it might still work out fine. But that's part of what this experiment's going to tell us. So it's pretty simple here. You can see it actually, it has a built-in A to D, built-in multiplexer, amplifier. It also has a regulator for generating a separate stable analog supply for driving the excitation voltage across the load cell. So pretty nice little integrated solution. It has a selectable rate, so you can measure either at 10 samples per second or 80 samples per second. And those are both kind of lower than our motor control loop, but given that this is being used mainly for kind of, you know, slower stabilization kind of stuff for like balancing force across the different chords, and for just detecting fault conditions like it's snagged on something, then I think that's probably fine. If even the 10 per second rate is probably fine, although the 80 would be a lot nicer. So one thing that's a little bit weird about this, it has some settings that are programmed by giving it a different number of clock pulses. So you can give it either, so to start with, it has a 24-bit signal. So you start out by reading out the 24-bit data signal. But then you send it a 25th clock pulse, and then it's kind of a stop bit. But then you can continue to send a couple of extra clock pulses, and it treats that as a configuration command, basically. So the next sample that it takes will be done with a different gain or channel. So it supports these 3 different configurations. So we need to support this scheme, at least insofar as only sending exactly 25 clock pulses when we read this out. But we do actually want to configure the rate. The issue is the rate is actually configured by setting a dedicated pin. And that pin actually, so, you know, it's pretty common for these really low-cost breakout boards to just be a copy of the reference PCB in the data sheet. And in this case, the reference PCB has the rate tied to low, which is 10 hertz. So yeah, they did the same thing on this board. If we take a look at it, here's the HX711, and oh, I'm about to sneeze. Why? I've definitely been getting the seasonal allergies again. So that's our rate pin, and you might be able to see a trace leading off to the left, and that's actually just tying that directly to ground. So I think it's probably worth trying this at the 10 hertz rate just to see how well that works, but assuming we want to change that, that'll involve probably just lifting this pin and then bridging it over to this pin, which is the digital power supply. So that'll select the higher sample rate. Otherwise, this board seems to be fine. It's got the transistor for the analog supply. I don't know if we have the capacitor for the analog supply. Are we missing that? That might have been omitted. Maybe we have to... That's weird. The reference schematic has a 10 microfarad capacitor between E plus and E minus. So we might want to add that externally. That would be to smooth out the regulated power supply, which clearly this board didn't care about. These seem fine. And there's our serial interface. So, let's see. Let's just hook this up and see if our driver gets us very far. I think maybe the next thing we need to know is what the wiring is on this particular strain gauge. We can just figure that out with the multimeter. Oh, I wanted this one. Sorry about the flicker. So, this is just a resistor bridge. So just like a diode bridge has that diamond shape, this is a resistor bridge. You can use it to turn very small differences in resistance into a small voltage, which this A to D converter then amplifies. So you can kind of almost see what's going on based on the order of the wires here, but let's just see what the resistances are between these pairs. So it looks like black and green are next door to each other. $750 ohms. Okay, are these connected to the other half too? They are. Let's make a little diagram up in my, my acquired copy of DaveCAD. Some of these are the contrast kind of stuck. I've got others that have a better screen. Okay, so we've got green, black, yellow, or white, red. Oh no, did I drop this tweezer? I think it's fine. That was not good. Alright, green and black. Just try to not affect this too much with my fingers. Yeah, 750 between green and black. $750. Alright, let's do the next two, black and then white. Oh, I had an extra window open. black and white is another 750. And then white and red. $750. Okay, what about red and green? $750. Cool. Might see where this is going. At least I hope we see where this is going. So then, I think if I go between, say, black and red, we should see double that. Or, no, it wouldn't be double that. We'd double that and then that in parallel again. So, black and red. That's 1K. And then between green and white, cool, 1K. So based on the measurements and potentially confirming with the color codes making sense, I'm going to guess that the black and red are the excitation, in other words, the power supply voltage coming in, and then green and white are the sense voltage. So this is, I guess, one way of drawing what we just did, but another way would be if you think of this as kind of a diamond shape, and then resistors between each leg here. Let's get that on camera. So then, let's say this is red, that's black, green, white, or something like that. So then the way this works, each of these resistors is around 750, but there are going to be very small differences depending on the mechanical strain of the gauge. So you put a voltage across red and black, and then measure very small differences in the green and the white. So I think that's how we want to use this. Let's get this, let's just take this separate little setup and tack it down, since that'll be a little easier than trying to experiment with the fully partially assembled robot over here. Especially for hacking around on this sensor and lifting pins. Oh yeah, and I'm going to go ahead and put that filter cap on the excitation voltage, because I don't think there's any reason not to have a filter cap on there. This might be a good job for a little radial through hole. Like, the data sheet said 10 microfarads, so let's just give it one of those. I've got one. And we can just kind of hang that off the edge of the board like this. Just like that. Get this all viced up. And I'm going to go ahead and trim the back side a little. Tack this down a little bit and then add the wire. Focus. Just gonna have the sensor and the capacitor share those pins right now. And then this has two channels, A and B. Channel A is a little bit more flexible in that you can, I think the way they did it is you can choose either a gain of 32 or 128 on channel A and 64 on channel B. So I'm gonna assume I want the higher gain right now, but we might end up wanting to switch this around if things get easy to saturate. So here, the sensor is basically fully differential, so it gives you a signed result. I don't think it matters what polarity I put this in. It's pretty easy to just negate the result in software if I need to. These might be easier to solder from the bottom side. I'm going to try to hold that down with blue tack. Maybe just bending the wires over will do it. Start there. Yeah, I'm sure this was copying the reference schematic because they went out of their way in the reference to make it single-sided. And here it's like a double-sided board with a ground fill on the back, but the front side is just a rip-off of the original single-sided artwork, basically. Oh, sorry, that was completely off camera. Well, about ready to hook this up to the scope and see what's going on there anyway. Actually, while we're soldering, I'm just going to put some headers on the other side to make that easier to deal with. ground plane. All right. Okay, cool. Got ourselves a little amplifier A to D converter thing. Our strain gauge. And then here's our microcontroller. The USB port is connected to a debug interface, which is currently just running on the Raspberry Pi. And then Ethernet is the bot network, which is also connected to the Raspberry Pi. Alright, and that's just the telemetry we're getting from the firmware that happens to currently be loaded on there. Let's take the scope away for now. So let's just see if we can run the firmware that I've... so I've been hacking on this a bunch and have a bunch of untested code in the repository right now, so let's just see what happens if I run the firmware that's currently in the repo. That's right. These build scripts name the outputs according to what compiler you're using. Okay. Also want a serial port open. Oh, it is in a halt loop. That is, that little scream there is the hard fault interrupt handler. So we have a little debugging to do. We could attach an actual debugger and just look at where that's happening. It might be quicker just to, first of all, just disable the things that I just added and see what might be adding or causing the problem. I don't know. We could try the debugger. So that would involve... Yeah, this little program called LMICDI is the GDB bridge for this particular debugger interface. Yeah, so if I just run this with root, and then run GDB with the binary that we have loaded on this particular bot. This is actually just an ELF file. That's right. Is this going to work? It's also possible this isn't going to work because of the watchdog timer. Let's try resetting this. Yeah, this might be the watchdog timer making things annoying. Alright, it might be easier right at this moment to do this with trial and error debugging. Let's at least get the source code mounted, if it isn't already. I guess it is. So I think everything that might potentially be failing would be in here. Let's just stub out this entire function right now. Okay, and now it's booting. So it was definitely something in that function. And so a hard fault error, there are various reasons that can happen. It's, it's like kind of a generic, you did something that's kind of outside the bounds of what the processor allows in this particular mode. I think the most of the hard faults that I get are for accessing memory that doesn't exist, or accessing peripherals that are turned off. So that might be what's going on here. I'm just going to check to see if I'm initializing all these peripherals that I'm using. Also, since I was hoping to just look at the force sensor stuff right now. I might just comment out everything here except for the force sensor initialization. So I want this force in it, and I'm just going to worry about whether the rest of this stuff is crashing later. Okay, so the force sensor thing is fine. Let's see what's going on in there. This is also totally untested code. So this thing, you initialize it, tell it what clock you're running at, what clock rate your system's running at. You give it a buffer where you expect it to place the results. If you look at the protocol definitions, you can see that buffer, in this case, just contains a signed integer, which is our A to D converter measurement, and then a counter that just increments every time we get a new measurement. And then inside the implementation of that, you can see that we're actually using a couple of pieces of hardware. We're using one of the serial engines, in this case SSI3, and we're programming the GPIO that's attached to that data pin to also have an interrupt when it's in the low state. So we use that to get notified when the A to D converter is ready, because it pulls that line low, and then we have to clock out a bunch of bits, specifically the right number of bits, probably 25 bits, because I think we're going to want to use this mode, where we're in channel A with the highest gain. So yeah, we're generally waiting for the data line to go low, then clocking in 25 pulses, the first 24 of which are being stored as bits, and then going back into the mode where we wait for the data to go low. So we can just hook this up and see if any of it works, and then debug it. Yeah, I'm pretty excited about the idea of a Tuco cam that can just hover. All right, got some jumpers. Ready to jumper these boards up to each other. Isn't that exciting? So this is just a unidirectional SPI bus, basically. It's just a little bit weird in that it also uses the data pin as an interrupt pin, effectively, because between transfers, the host has to wait on the data pin to go low. So that's part of what makes this weird, but otherwise it seems pretty normal. So let's rely on this README. Winch A2.7 and D2.7. Okay, they're on this side. This will be my ground. And I can power this off of 3.3 or 5, so let's do 3.3 so the logic levels are compatible. Then clock PQO. Data, finally, PQ3. I'm looking at these labels that are silk screened on the bottom of the board, which are kind of handy, but also kind of awkward. I mean, it's handier than not having them, but it also involves turning the board over and doing some mental geometry to project them back onto the right plane in the right orientation. Oh, I don't have... This board is not littered with grounds yet, like the other one is. Okay, that's fine. Actually, no it isn't. I want grounds. I was going to skip out on all sorts of other things, but having sufficient quantity of ground terminals is not one of them. I will switch to the other soldering iron for this. The one I was just using was the micro soldering tip, which is really good for small stuff, but not what you want to be using for ground planes. It's just not fun. All right. My plan to break these out for O-scoping was to put some additional headers in the bottom to get the signals I want, and then for grounds to just populate some of the ground test points on the top like I did before. That's a happy cat. You really never have too many grounds. Clearly on the, those fancy boards that have the machined RF enclosures, they should just like machine in little alligator clip grounding points all over the place. Is there any more on this side? There's one. Really don't want this pin to go into my finger. Now that I've said that, it almost certainly is going to go into my finger. Oh, different outcome. I bent the pin. Well, now I have to get another one. I don't necessarily need this many grounds on all the robots, but at least the ones that I'm messing with on the bench a lot. It doesn't hurt to populate a bunch of the ground test points. I mean, I don't know how much fussing this is going to need. It might be pretty simple. I suspect I'm going to need to do a little bit of fussing on this one, and then I'll just build 3 more once I've got the basic design debugged. Oh, this iron has a relatively big tip in it. It's a very big difference from the micro soldering tip. Oh, there's one. Oh, good question from DevFlame in chat, who asks how many winchbots will the final implementation use. My plan was to have 4. You need at least 3, and 4 gives me 4 vertices, so I can position the flyer within a square or a quadrilateral. So yeah, 4 winchbots. Although, yeah, the architecture I expect will be pretty arbitrary. Like, I mean, I might end up having to make more assumptions once I get into actually writing the motion control code for the overall system. But the individual bots are all pretty separate, and they all run the same firmware image. You just set the EEPROM up to give them different IP addresses and different configurations. Okay, that's a comfortable number of grounds, perhaps. So, yellow and green. Okay, so that's scoping out the clock and data on the serial bus going between the micro and the HX711 force sensor strain gauge A to D converter chip. This is basically a digital scale on a chip, or at least the analog front end for one. The idea is that you'd add a really cheap microcontroller and LCD interface to this and get a digital scale, but in this case I'm using it for a sensor on my robot. And then so those wires go off to a little strain gauge. Oh, I'm getting a little blip on the scope already. Let's get that on the screen. So that should be right with yellow indicating clock and green indicating data. Got a trigger on that? That might be my sample rate. 10 samples per second. A little faster. So when that pin is in the low state, that means that it's ready for me to read back a sample. So it looks like what's happening is I'm not actually getting around to reading anything, and the sensor is just very, very briefly becoming unready, probably while it's actually taking a sample. So I think I just don't have the driver actually, like something isn't enabled so that it isn't getting to the point where it's taking any action based on this being low. Because that should be triggering an interrupt, which should have me doing additional stuff. So let's see what's happening on the code side, maybe. It's also really tempting just to go ahead and hack that into 80 sample mode right now. But let's see if we can get it working on 10 sample. Let's also organize this. I figured today I needed to wear my witch hoodie because we were doing some hexing with the HX711 sensor. I mean, we usually end up doing some hexing. Usually the hexing is slightly different, involving editing of hexes. In this case, the hex comes in a small breakout board. Okay, so this is the driver we have so far. So we should be initializing this GPIO port in a mode that gives us an interrupt anytime it's in the low level state. It should be happening. So, hey there, train. So let's maybe let's disable this temporarily just to make sure we aren't seeing any actual results, and then let's temporarily use the result counter as a debug tool to see if we're getting any interrupt invocations. And specifically, I'm interested in this data pin IRQ since that's what we should be seeing first. And where does that end up? So that goes to force telemetry counter, which is pretty much at the beginning of this winch sensor structure, which is right there in the winch status packet. So we're going to have to unpack that a little bit. There will be a command counter, a tick counter, the most recent command, then the current sensor reading. But it should be pretty obvious if something is incrementing inside there. That'll be near the end of the packet, and nothing else in here should really be changing much. This serial port is not the amazingly happy serial port that I sometimes wish it would be. But I don't really need the serial port right now. Oh, I should just change this one. Yeah, I know. It's not a good password. That's fine. Oh, whatever. I know. I could do that as root, but maybe I'll just keep trying to type this long one. That's better. I thought I saw something change on the scope. Huh, no increments at all in there. I'm used to seeing some, but I guess those come from the motion controller, which I have commented out right now. Yeah, that whole thing is commented out. So, yeah, nobody's getting an interrupt. Why would I not be getting an interrupt? Oh, did I not int enable that one? Or just that? Oh, that comes up here. So that, and that's the first state I enter. So this is the kind of one-time initialization, and it finishes up by doing a state transition. This is a simple state machine, and it goes into the state where it's waiting for the data to go low. That's where it initializes this interrupt. Let's just simplify this by also turning off the SSI peripheral, and let's only be looking at the GPIO behavior right now. Because I don't think this multiplexer affects the input behavior. At least that was my reading of the datasheet and my experience with this in the past. But just for simplicity, let's comment out some of this stuff. I think that's all we want. And then down here I'm just commenting out that state transition, because I just want to count these. Is it possible that this doesn't work like I expect it does, the low-level interrupt type? Also, maybe I can find an example of this somewhere and see if there's a step I'm missing. Okay, well, this logger example sure has been useful for a lot of the hardware. That was also where I learned how to use the A to D controller sampling engine. So, GPIO pin type. I guess I didn't do this, did I? Let's try that temporarily. I don't know if that's actually what I want, but... I mean, worst case, I could bridge this to a second pin that I configure as an interrupt, but that seems a little weird. Like, I don't think I should have to do that. And they're doing int typeset. I'm using low level. there's GPIO int enable. Oh, they're using this one slightly differently. Port B base pin 2. I'm using int pin 3. What are the differences between those definitions? I think we would find that in the GPIO driver lib over here. I think these are interchangeable. I think the difference is that this has an extra constant for DMA, but I think otherwise these are the same. Oh, or maybe not. Maybe these are off by 1. No, I think those are the same. Okay, I guess that difference is inconsequential. What about these edges? You know, I guess I don't have to worry about the low level. So I was worried about it being a level triggered interrupt because I thought that maybe if it was already ready, then I would need the level trigger to notice that. But it looks like if it goes periodically unready, even if I don't read it, then maybe an edge triggered interrupt would be fine. Oh, where am I at? Low level. Let's look at the data sheet, maybe. Oh, excuse me. Turn off that camera. I don't know why I wouldn't be getting an interrupt. Oh. Just noticed a question from the YouTube chat that I'm having a little trouble parsing. They're asking, I wonder how you happen not to grill everything with all the threads you can solder everywhere on the microcontroller. I mean, it takes some practice to not make things worse when you're trying to modify something or otherwise get in there and mess with it. I don't know, but a lot of the answers you do oftentimes make mistakes, but then a lot of the time you can fix them. Like you make messes with the soldering iron and then you can clean them up. And it's a little less common to actually destroy parts, but when that does happen, you know, you move on. You try not to work on stuff that's irreplaceable. Let's see. Did I test what's actually on here yet? Am I seeing any increments? no increments. So that comes from forced data pin IRQ, so we're not getting here. We would expect to get there from the interrupt vectors. If we were getting an interrupt but going to the wrong vector, then we would be hitting one of these unimplemented ISRs that would be getting us stuck. And we aren't getting stuck, we're just not seeing that counter increment. So I think we just don't have this IRQ enabled somehow. Q3. That should be this front pin. Oh! This might be an issue with this dev board. I think this dev board actually lets me switch this between PQ3 and PA2. Maybe I have to switch something. Let's look at the schematic for this dev board. So PQ3. Yeah, PQ3 and PA2 have something weird going on. Looks like PQ3 is the default. So that's labeled PQ3. Yeah, it looks like, where's that resistor, R20? And it looks like it's an option, and the way I'm using it right now should be the default. Ah, pardon me. Ah, much better. Oh. R20 and R19 seem to both be populated. Okay. So PQ3 and PA2 are connected to each other. Where else does PA2 go? Okay, maybe this is fine. Maybe they're just bridged and I can ignore PA2. Oh, wait, what? Debug? Oh no, this is the other microcontroller. That's the ICDI interface. Yeah, this is the micro we're talking about. Okay. I guess that was a red herring. Port Q. PQ3, right? Yeah, so that's the green trace on the O-scope. Should be PK or PQ3. So we've got something that should be giving us an interrupt. What about the interrupt levels? I mean, I could try edge triggered. I just don't think that's what I want. I'm just looking at these functions to make sure I'm using them right. This is the little wrapper layer that they provide around the registers to make things a little bit easier to read. I think that's equivalent, but I might as well use that for consistency, that int pin. Maybe one thing I'm fuzzy on is what the difference is between enabling a summary interrupt versus a per pin interrupt. Who sets this flag? Oh, I think I need this flag. Do I need this for the port as a whole? Int type. That goes into the SI register. Now I'm just wondering, do I need this, like which of these do I need to set this flag in? Yeah. So this is set per port. P and Q. Okay, so I can just do this on any of the pins on that port and it'll handle setting it for the port. So I think that's all I needed. I might just need this flag and then maybe it'll work. Low level and discrete int. We'll keep all this other stuff disabled for now. So what I would expect to see now is that this counter will just continuously increment as long as the pin is low, which might end up hogging the CPU enough that we don't end up sending packets. So that might be another valid result here. But what we shouldn't see is nothing. That looks a lot like nothing. Okay, so that was in int type set where we just were. And then int enable, we're using that right? That's pretty straightforward. It's definitely something programming, especially with embedded systems, has in common with those old adventure games where you just had to look for just the right pixel you were supposed to click on. There's just something really simple, I'm sure, that's keeping this from working. I'm just expecting to end up here. If I end up in the interrupt handler at all, a variety of things could happen. I could see this counter being incremented, I could have it crash, it could like hard fault, it could infinite loop, it could starve the Ethernet thread and it wouldn't be able to send packets. Any of those are fine. I just want it to do something to indicate that I have the interrupt happening. I wonder if I can find any examples for using this discrete interrupt flag with their library. Yeah, I agree with what Kyle says in chat. This is simultaneously my favorite and least favorite part of development, getting to reverse engineer your own system to figure out exactly what's going on. Yeah, that's definitely been my experience in the common link between creating things and taking them apart, is that in creating things you have to be able to take them apart along the way. It's just sometimes annoying, because sometimes you just want to make something. You don't want to have to keep taking it apart again, but that's what happens. And enable. I feel like I'm probably just not using this right. I mean, we don't have to use this discrete integer feature, or discrete interrupt thing. It's just the chip had a separate interrupt for the pin that I was using anyway. We could also just kind of monopolize that entire port's IRQ line because I don't think anybody else in that port needs it. Oh, I could ask Google about this flag. Oops. Is this relevant? It looks like maybe this API function was not even originally designed with that feature. Ash asks in chat, would you be interested in extracting the firmware from the Dreamcast's GD drive board at some point? I mean, I don't know. Maybe. I don't really have a specific interest in that. I don't know. I mean, that seems like one of those projects that would be a little bit interesting to me, but not that interesting to me. Would probably be more interesting to pirates, which, like, I'm not really into helping people make piracy tools. But if there's just like an interesting reason to take that apart, then maybe. But like right now, my intuition is that it's not probably a super high priority project. There's probably more interesting stuff to take apart. Okay, can we not use this? Oh, interesting. So the GD boards have some test points on the board for serial, but it seems to spit out like servo or something like that, servo data. Okay, interesting. That might be an interesting project one of these days. Oh, maybe the soft UART's a good example of how this might be used. Yeah, it might just be that this driver lib does not really have good support for the individual pin interrupts, and so that's fine. I think I might just retool this to use the port-wide interrupt, because I don't really care that much. But that doesn't really explain, like, if the problem was just that this was routing it to the wrong interrupt vector, then we would be crashing. Like, this is acting like the problem is elsewhere. And this all seems to be pretty unsurprising use of the API. Well, we could try falling edge. I guess we still haven't tried that. Let's give it a shot. Well, no crash, no increments. That's still not what we want. Oh, we are getting into this initialization code, aren't we? I'm just gonna, out of paranoia's sake, put something I know about in that buffer. Just see if we can see that in the output. Also, there's no reason to keep stopping the telemetry receiver. Okay, those are the packets. So the packets stop. And then there's the thing we just put in the buffer. So we are getting through the initialization. This isn't like just magically getting skipped somehow, but we are not getting our IRQ. So pin type, GPIO int typeset, int clear, int enable. I don't think the clear is actually necessary there. That's, well, if you're coming out of reset. I mean, that might be helpful if you're doing this not out of reset. I guess we could clear the interrupt. I don't know if that would make any difference. That's the only thing I'm seeing that's different in the API usage here. Yeah, why am I not getting an interrupt at all? It's back to the zeros. Still no IRQ. The scope is showing that pulse. Could it be a logic error up here? Are we not getting to this int enable somehow? Mikhail is asking for a recap of what's going on. I'm just debugging firmware. There's the cat. So the firmware for the flyer bot is pretty much fine. I put the flyer aside and I've just got to do some CAD on it to get that up to speed. So I'm starting to debug some of the stuff that I've written for controlling the peripherals in the winch robot. So the biggest thing that I'm trying to do here is test the driver for this HX711, which is an A to D converter that I can use to read the strain gauge that measures force on the winchbot. So I've got a little example set up here, which just has one of those A to D converters, one of these strain gauges, and then the microcontroller. So I've got the firmware loaded on there, and right now the problem I'm getting stuck on is I've got this thing mostly written, I've got a lot of it disabled for testing. The thing that I'm getting stuck on is I'm not getting a GPIO related interrupt, so I'm trying to have an interrupt wake me up when this thing is ready for me to read a sample, which happens when it drives the data pin low. And so I'm just not getting a GPIO interrupt. I'm trying to figure out what's going on there, and now my mouse is having trouble. There's my mouse. So do we know we're getting here? Is this the right interrupt? I think this suffix is unnecessary, but I think otherwise this is right. Let's just make sure this compiles without the suffix. Yeah. That was just an artifact of how the header files work per part. Pin Q3. So we wouldn't be getting any interrupt at all if we were enabling something that isn't the actual interrupt here. So if this int enable is wrong, or if this int enable is wrong, and so maybe let's check over this constant. Oh, that was maybe missing something. Int device class. Maybe that was the problem. Oh, no, I think that's just a preprocessor thing. I think that's just copying the value. But if I was using this, that's not the chip that I'm on. This is the right chip, so that might have been the problem. Is that actually what's going on? Do I have a diff for that? Yeah, that was the wrong chip. That might have been the problem. Let's see if I can crash it now. I'm looking for a crash or an increment or something that isn't just this stream of zeros. Ah, increment. Nice. Why are we only getting one of these per measurement? Now it's acting like it's edge triggered. I wanted it to be level triggered. Oh, because I made it edge triggered. Let's see what happens when we make this level triggered again. What was that called? Low level. It really helps if you use the right definitions for the processor you're on and not a different processor. Just one of those little embedded tips and tricks. All right, now this might be the crash I was looking for. The reason I would expect this to crash is if that signal is almost always in that low level, then the interrupt handler would just keep getting re-invoked and we wouldn't have time to send any network packets. So I think that's what's happening. At least that's consistent with that explanation. So let's see if we can make a little bit more progress here. So let's just turn some of this stuff back on. I'm going to try turning on the SSI stuff so that we actually try to start a serial transfer when that interrupt occurs. Okay, I think that reverts all my flailing around. So now when we get that data low IRQ, which means that it's ready for a transfer, we'll do the state transition, which ends up turning off this IRQ for now until we're ready for it again. And it begins an SPI transfer for the first 16 bits. And when that's done, we'll get this other interrupt, this SPI completion. And so when we finish the first 16 bits, we'll do another transfer to transfer the rest of it, which is kind of a weird number that depends on this. So in this particular setup, it'll transfer 16 bits and then 9 bits to get a total of 25 bits. And so after it finishes that second transfer, we end up here. And again, we store the results. And then we go back to waiting for the data to be low, which re-enables that initial interrupt. So let's give that a go. Oh, that's a good sign. That's a really good sign. We've got counts and we've got pulses. Well, that looks about like what I was expecting. Cool. How many clocks is that? Yes, I know. Cursors. So that's 8 clocks. 8, 16. So that is the first 16. Cool. Then we have 8, 8, 9. Ah, and then we have a problem. So this is what we expect, but then we've got a second, like a duplicate transfer over here. So what that might mean is that it isn't detecting the data going back high early enough. And so that might actually be a symptom of something being set wrong with our SPI settings here, because it should be giving us data high before that last bit. So what's happening over here? Is it also possible maybe that I'm issuing the first clock too fast after data goes low? So that was the first 16 bits, and you can see the bits are changing. Let's zoom in there. So the bits are changing on the positive going clock edge, and we're going to want to sample them on the negative going. So if it's sampling right after that last pulse, then yeah, that should always be high. So, oh, maybe we just need to clear the pending interrupt before enabling it. Maybe that's what's going on. I bet that's the problem. Because this will matter, like if we end up with any high state or any low state during that SPI packet, which of course will exist, then it'll end up setting this sticky flag that I think we need to explicitly clear before we enable the interrupt. Is that what we want? This is just going to be the same line, but we need to do this before enabling the interrupt. Let's see if we can fix this. Nope. SPI end of transfer. Wait for data low. Oh, maybe I should disable SSI. Yeah, that seems unnecessary. I should be able to keep the serial port enabled and just not send anything to it, you know. It would be nice to add a little bit of like printf debugging or otherwise so I can see if that's actually re-entering the original state or if something else is going on. This would be a good time to use just oscilloscope debugging maybe. Maybe we'll combine the two and do oscilloscope serial port debugging. Oh, that's not the button I wanted. Sorry about that. I accidentally hit that somehow. That's the serial port where I've got some periodic status messages, and we can also put some debugging on there. should solder this header on, but maybe I won't. Okay, so right here, I'm going to print something really simple. I have to be a little careful with these because if the buffer fills up, then it's just going to end up dropping stuff, or will it block? I think it drops stuff instead of blocking, but I don't remember for sure. Either way, it's not good in this case. So I'm just going to print something really little. I'm looking up the name of that debug function. uartprintf. What did I have? Oh, just uartprint. Ha. Flash. Oh, there's some serial. Let's decode that. Oh, SPIs, don't use that signal. Not decoding. Oh. No, that's not a useful threshold. Oh, look at all those state transitions. All right, so we're going into state 1, then 2, then 0. All of that is expected, but then we're doing it all a second time. So that confirms that we're just doing this twice when we shouldn't be. So it might just be that we need a little bit more delay before the high logic level is actually going to get detected by the interrupt capture part of the GPIO hardware. Make sure we're using the right SPI mode. This is mode 1. That's the diagram I wanted. So clock polarity in this case is 0, and this is about which edge is relevant. It looks like in every case, the positive edge is going to cause it to shift in a new bit, and then I want to read it on the negative edge. So I think that's clock phase of 1. So I think this is in the right mode. Okay. That's just something I wanted to verify while we were here. You know what's probably going on is I think I'm probably getting... No, that doesn't explain it. I was going to say I'm probably getting this interrupt too early before the transaction's actually gone out, but I know I'm getting this after the transaction's finished if I'm getting data to read. Maybe the read data is not working. Have we verified the read data is working? Because maybe the interrupt is just coming back when the data has been... Like maybe I'm getting an interrupt when the SPI starts transmitting the last word, not when it finishes transmitting. Oh, it might help to move some of our debugging in this case. Let's ditch this and instead start something when the SPI finishes. Like, let's ignore the first 16 bits. Let's put something right here. Let's just put a little one-character marker. Okay, so that's happening twice. The thing I'm most interested in is the timing of the first time. That's well after the transfer's done. I mean, we might be seeing some delay due to the due to the serial port not being very fast. One thing that might be useful to do, I mean, we could switch from serial port to just like GPIO debugging. That might be the easiest thing to do. Could also have that UART print include the pin's current state, but I think I'm just going to go snag a GPIO for debugging purposes. What's easy to get? Oops. EM7. Okay, blue wire should be on PM7, which I chose pretty arbitrarily. And let's put some temporary stuff in here. So we need GPIO-M. let's just have a really little blip here. And since this should be smaller now, let's do it on every SPI IRQ, not just the last one. Oh, I want that to be output too. Flashing. There we go. Nice little spikes. Well, it seems very done when that happens. I mean, one thing that comes to mind is just adding a delay, and an easy way of doing a delay without taking any additional hardware resources would be to do like a dummy transfer with the serial port with the clock disabled and just ignore the results. But I'm confused about why a delay would be necessary, so I'm not going to rush to that just yet, even though that might actually fix it. Yeah, maybe what does the data sheet say about latency on these edges? Like how long does that GPIO need to be high for before I enable the interrupt to avoid getting a spurious interrupt? Maybe there's also somewhere else I need to clear this. Like, do I need to clear it in the NVIC, the ARMS interrupt controller? I mean, I can also just check to see if the pin is low when I'm in the interrupt handler, and that might actually be what I need to do. Because that would protect me from various kinds of spurious interrupts happening and ruining my day. Let's try that. That's a pretty easy fix. So I think we want GPIO read, or pin read, yeah. Sorry, I was typing behind that. I want to check to make sure this pin is still low. Oh. Sure, that can be a pin. That can be a pin anytime. That looks nicer. Cool. So that's happening every time a conversion's done, so about 10 times a second. You can see it change when I'm picking this thing up. So I'd like to actually hook this up to a little Python script or something that can graph it, but that's going positive, it's going back to 0, and then negative. So actually, we can look at the timing for that first bit by having it go negative. Yeah, so the data line goes low, so the green trace is going low initially to indicate that it's ready. And then it goes high again as soon as I start clocking out the first pulse, and then it's ready to read when that pulse goes back low. So that's all looking good. So is this going out over UDP yet? Doesn't look like it. Why not? So over here, I'm reading from the SPI data FIFO. Is that all zeros right now? Those get assembled by this function, HX store result, which just does some bit shifts to put all the bits where they belong. So, is it possible that the SPI is in write-only mode? I have to tell it that I want to read also? Oh, QSSI direction of operation, transmit mode, receive mode. Maybe I'm just using the API wrong then. So if the hardware is in transmit mode. Yeah, this thing here where I'm doing SSI data put non-blocking, my intention is for that to be a dummy read, or a dummy write that initiates a read, but maybe the API is taking that to mean I want it to be put in transmit mode. So let's verify what that's doing. SSI data put non-blocking. Yeah, that doesn't change the configuration. So that's probably fine. End of frame. Okay, this is for the high-speed protocol. This is not useful right now. Oh, is that only for quad SSI? No, I doubt it. DIR, bit 8. In control register 1. So who's messing with that? Oh, is this setting the direction? Oh, advanced mode. I think we're already in the mode we want. Legacy mode should be full duplex. I mean, we should check to see if this is returning any data. So this get function, I think it'll return 1 if there's actually some data there, 0 if not. Okay, well I am getting data, it just seems to all be 0. Data get non-blocking. DR. Is it possible there's any junk in the FIFO? Let's make sure these are initialized to 0. I mean, the static always would be, but the local variable wouldn't. Which isn't related to the current problem, just something I noticed. Yeah, so Mikhail's question is, are there separate receive and transmit FIFOs? Yeah, there are separate receive and transmit FIFOs. That data register, when you read from it, it's reading from the receive FIFO, and when you write to it, it's writing to the transmit FIFO. So the way my understanding is that this works is that you write some dummy data to the transmit FIFO, and that causes both a transmit and receive to happen simultaneously, and then the resulting word that you received goes into the receive FIFO. So we verified that this interrupt is happening well after the transmit is done, and this is returning a successful error code or successful result code, which means that the hardware register said there was some data in the FIFO. So I also just noticed a question from Max in YouTube chat who asks, is this real life? What's with the cat? Well, it is. There are cats in real life. And then I guess there was an earlier question I missed about about the GPIO interrupt registration. I'm not using int register, if that's the question, because I don't have my interrupt vector table in RAM. Those functions are only relevant if you're using a RAM-based IVT, which is like something that some of the TI example code does, but not most of it as far as I can tell. And so I just thought it'd be more straightforward to have a plain old flash memory-based IVT. Oh, we got a $2 super chat from John. Thank you so much. Well, so I mean, this is pretty close. We've got the timing and everything working out just fine. We just have some data that we can't access. Apparently it's all zeros. Just debugging this. So I have this little GPIO debug blip, which I think I'm going to move into the HX store result function. It'd be nice to know, to just verify what the arguments to this actually are. So maybe let's comment out most of this and have a simpler version of this that just stores what we're getting. So I'm just going to store the remainder buffer right now and ignore the first 16 bits because I want to see what this looks like in full 32-bit width just in case. And I'll still have the counter. So now I'm going to expect to see a little oscilloscope blip once when we're done storing the result, just to make sure this is actually getting invoked when I expect it to. And then this will be the 32-bit wide contents of the SPI receive FIFO that we were reading earlier. You know, it's just acting like the SPI engine doesn't have its input pin routed correctly or something like that. So I should double check the pin routing. PQ3, that should be this up here. Oh, and then I'm overriding it with this. That's right. Let's take this out, because I don't think this is actually necessary. Because the GPIO interrupts should work even when the pin isn't being controlled by the GPIO hardware. At least that's how I read the datasheet. Let's see if that works. Oh, that looks like a good sign. We're getting increments and non-zero data. Oh, that's great. Let's put this back to how it's supposed to be, I think. Let's remove this temporary thing. Have the store result hopefully operating correctly. So that function will assemble the two partial reads, that first 16 bits and then the last 9 bits, or the last 8 bits, and sign extend it to 32 bits. All right, that's looking better. All right, so there's the microcontroller. Here's our Ethernet. The results are coming in over UDP packets here. So this is just an incrementing counter, but then you can see it increments every time we get a measurement, which is currently 10 times a second. So you'll see right here on the same packet, the counter increments and we get a new measure. And so if I push it in one direction, the numbers should go one way. Okay, so now I've got negative numbers. FE, FD. The high gain is probably what I want because I can push this pretty hard and it still seems like I have plenty of dynamic range there. So that's going negative, and then that direction it can go positive. Sweet. Well, I think I picked a reasonable polarity too, because positive is the direction that the force is mostly going to be exerted along. Well, that's great. So it can easily tell the difference between a totally slack line and a line that's stuck on something and a line that has an acceptable amount of tension. So I think maybe the two things to try now are maybe it'd be useful to graph this. It would also be useful to try increasing the data rate to 80 samples. Oh, I see Mikel is suggesting graphing it in Python. Yeah, I was just wondering, like, what do I graph it in? And then the question is, well, what do I want to graph it in eventually versus what do I want to graph it in now? I still don't entirely know what shape the firmware, or not the firmware, but the overall bot controller is going to be in. It's tempting to use it as kind of an introductory process or project to learn Rust with, because, you know, I was kind of shying away from running Rust on the microcontrollers because a lot of that is still really up in the air, and the libraries that I'd be relying on probably wouldn't be stable in 6 months. But the PC side, I'm sure that would be fine. I'd just be doing network I/O mostly. But then as for something that works right now, I mean, well, what, do you know something in Python that would just let me have like a really nice low latency graph here? I mean, matplotlib, that kind of thing exists, but that's not real time in my experience. There's like a Pygame, which would work, but I'd have to write a bunch of stuff, kind of boilerplate stuff from scratch, and it'd be annoying to run cross-platform. Similar story with like WX widgets or GTK. There's smoothie charts, which is what I was using in JavaScript for the winch, or for the gimbal, and so that might actually be a really easy thing to do. I could also just dump out a CSV file. I don't know if I need this to be interactive, although that would certainly be nice. I'm going to want an interactive chart for the motor stuff really soon, so I should probably plan ahead for that. Well, let's start out by just parsing this out just a little bit. I want to do the hardware mod for the 80 sample thing. So I would like to do a little bit of this and then maybe do that mod. I don't know how much I even care about seeing the data from the 10 sample config, though. I might just do the hardware mod and then worry about making it look nice. Because this is alright, but I think I care a lot more about update rate than precision. Because like, this isn't a postal scale, this is a robot, so having another order of magnitude of rate here would be really nice. So maybe this is a good time to do the mod. So you can take some of these cables apart. Wow, I'm feeling accomplished at having programmed the SPI controller to transfer exactly 25 bits on an interrupt. Like, that's the kind of thing where it's totally within the hardware's capabilities, but you're probably not going to find an Arduino library that does it. So it can really help to learn some slightly lower level interfaces for that kind of thing. All right. So if you were here earlier in the stream, you might have seen my explanation before. This is the HX711 that we were just programming a driver for. It's a 24-bit A to D converter and amplifier designed for digital scales. So it's working pretty well and giving us a nice number corresponding with the force on the strain gauge. But we can increase the sample rate by setting this pin, oddly enough the rate pin, from its default low state here to high. And the breakout board here doesn't make that easy. So we're going to have to lift a pin. Oh, nice. Vince in chat apparently also got one of these TI Tiva C boards and is enjoying it. Yeah, I mean, you know, I dislike large corporations as much as the rest of them, but it is certainly nice to have a piece of silicon that works pretty nicely. So, you know, I'm not going to be like a TI fan or whatever, but it's always nice to find tools that are satisfying. And I feel like this is one of those that had a lot of the same kind of silicon vendor annoyances that I'm used to, but, you know, with the right collection of bits and bobs from GitHub and kind of banging your head against the datasheet enough, managed to make it pretty decent to use at this point. Let's switch to the small soldering iron. Yeah, maybe let's do this soldering change, and then yeah, we can think about graphing and that kind of stuff, but I don't really want to get sucked into that right now. I'm in the mood to do hardware. So we can do software and graphing and stuff some other time, but let's make sure this works at 80 samples per second. And assuming that works, then I think the next thing I want to do is to try the quadrature encoder driver. That's what we're going to use to measure the position and speed of the cable movement through the winch. Not something to do with your favorite X-Acto knife tips, but... So I can't quite tell if I managed to clear that. I'm going to angle the microscope a little bit. Oh, John asks, so out of those 24 bits, how many would truly be useful? I'm hoping at least 4 or 5. Well, maybe we're going handheld. That is definitely not clear, but I think it just needs a little flux. Geez, how am I going to mount the microscope there? Get some more of those carbon fiber rods to mount my microscope on, maybe. Oh, that's so almost in focus. Maybe I need to adjust this. Yeah. Now it just needs to get a little fluxy. Maybe a little more separation. I think that shiny edge is telling me it's probably separated, but let's ask the multimeter. Yep. Great. Now, the pin we want to connect this to just happens to be right next door. So I'm just going to do something kind of like that, except maybe not with stranded wire. So some of this wire maybe. Oh, sorry, Vice. That needs to be trimmed, and then de-awfulized, de-uglified, de-terriblated. Ooh. Okay. It kept wanting to slide off of the pin sideways. I think it's now successfully soldered to the top of that pin, even though it looks a little gross. I think that's actually pretty much what I wanted. Yeah. Confirm it from the side. Let's just check that out with the multimeter, but I think that's going to be fine. Great. Let's see if we get 80 samples per second out of this now. Maybe I'll clean it off even. Definitely not the most annoying mod I could have to make to this board. Such cat. For it not to be quite so drenched in isopropanol when I power it on. Okay, I should put some of this back on the scope at least. Let's at least grab a data line so we can get the overall rate. And what do we have? Already seeing it change in the software, which is cool. Hello? That should be triggering. Why is it not triggering? Oh, there we go. Trigger level. Yeah, that's better. That's a little under 100 Hertz, which is what we're expecting. And I'm sure that the result is less accurate, but it's probably better for what we want. So now this is the counter. You can see now the counter is incrementing about every 2 or 3 packets, which is what we'd expect. And then this value, that updates nice and fast. That's great. We really wouldn't want it to go negative during normal operation, but yeah. Mikhail asks, are there super thin Ethernet cables, only 2 pairs or the full 4? They must be the full 4 because they work fine with gigabit speeds. They're really thin wire. They're 30 gauge wire. Yeah, they're patch cords from Monoprice. Okay, well I think I'm ready to call this driver done. And then it works fine at either rate, but I'll probably mod these all to work at the higher data rate. So the biggest change was this constant was wrong. That was preventing most of this from working. But then also preventing the spurious interrupts after the transfer is done was important. Gotta push this in case anybody's following along at home. Also because I don't trust the SD card on this Raspberry that much. Alright, well that's our first substantially complete sensor for the winch part of the bot. I mean, I had the driver mostly working for the quadrature stuff, but I just had it disabled just now because it was crashing. So I do want to take a look at the quadrature next. So I think the two steps there are re-enabling the parts of the driver that we need and actually connecting the encoder. I think I might want to connect the encoder next. And that might also be a case where, instead of connecting this contraption, I might just go grab another encoder so we can experiment without having all this stuff already wired together. Encoders. Of course, I say that assuming that I know exactly where the encoders are. There they are. Here's one. So these are optical encoders. I think they have open collector outputs. So yeah, we'll have to try that out. I also don't remember off the top of my head what voltage these like. I think they're probably fine with 5 volts, although they might be designed for something higher, and I doubt they're going to be happy with 3.3, but we can always find out. We did Google Translate these in the past, and I think the wiring was pretty straightforward. It was, I think this was, yeah, so the connections are all in, I think that's Chinese, but yeah, I think we tried this in Google Translate before and it was pretty straightforward, like red is power, and I think black was ground. I guess we can just do this right now just to verify. Google Translate. Well, we got shield. I don't know if we're going to get color this time. That's fine. I don't think we actually need that. I'm curious to see if we get continuity between the shield and any of these signal pins. No, shield is not directly connected to these. I'm curious if I get a voltage if I do diode test across the red and black, although I don't know if I would. It might be too high. It looks like there's a reverse protection diode at least. Let's try powering this. Let's just try giving it 3 volts to start with and see what happens. Maybe current limit it a little bit. Three volts, limited to 100 milliamps to start with. It is drawing 10 milliamps, which means maybe the LEDs are on. .3 volts, 10 milliamps. Yeah, I'm curious to see if this runs off of 3.3. It'll probably run better off of 5, but let's see if we get any waveforms out of it. I think we're going to want pull-up resistors. A weird, like, almost burned popcorn smell on the other side of the shop, which I think is coming from my neighbor's kitchen, but I always get suspicious about these things. Where's the piece of overheating something or other? Alright, let's get some headers. Let's just break these out, make room for some pull-ups. I'll try this without pull-ups, but I assume I'm going to need pull-ups. Get a couple of scope channels. so those are both low. Oh, and we're getting a little bit of jittering, but yeah, I think that wants a pull-up resistor or two. Maybe it is fine with 3 volts. That'd be nice. Yeah, those are seeming pretty okay at 3 volts. Cool. That's just fun. Yep, anyway, where do these go? Consulting my notes. So, encoder, 2 inputs. The quadrature peripheral also supports a 3rd input for indexing like a 0 position, but we don't care about that. We don't have like a 0 position for the nylon cord. So we're only going to care about relative motion. So PL1 and PL2. PL1 and 2. Let's go ahead and power this from the TI board. I think it can handle 10 milliamps. And then this little breadboard will just have the resistors. Inputs. Okay, that's connected. Let's see if we can get the firmware to work. Start enabling the stuff that I disabled before to avoid the crashingness. So I think this code worked. I think I've used this before. Let's just turn that back on. That should get us these IRQs, but I want to turn off most of the contents of these. So if that works, this IRQ should give us an updated position, velocity, and acceleration, and it should give us a count. But none of the motor stuff should be turned on yet. Oh, that's fine. Oh. Okay, we got our packets, no crash. Got a count down there. And that might be an encoder position. Oh, it is. Let's get that on the camera. So yeah, this number starting where the cursor is our signed 32-bit position. So that's just going to keep counting. So I can just spin it this way, and it moves that number in one direction. I can spin it the other direction. Should be, I think, 600 per revolution. So yeah, if I just spin it this way, you can see this number increases. You can also see another number here, which is going to be velocity. And then the third number here is acceleration, which is differentiating velocity. So I just spun it a little bit. You can see the counter. Velocity ramps up. Acceleration is mostly positive with some negative spikes. And then the acceleration is mostly negative for a while. So I think the quadrature is working. That's exactly what I was hoping to get out of this. I guess the next step is to see why the PWM code in progress was crashing, and to fix that. Cool. Well, this is feeling pretty good, successful so far. All right. So I had this thing, which was setting up the motor enable signal. That just seems pretty harmless. Let's just make sure this isn't crashing. This is just a GPIO that turns the H bridge on and off. And the way I was using this is to have it default to be off, but then periodically there's kind of a software watchdog timer, basically. So every time the motion control interrupt happens, we can evaluate whether it's still safe to run the motor. So if the force is out of the hard stop range, or if the sensor stopped working, or if we lost communication with the computer, then we can just turn off the motor and it'll coast to a stop. So yeah, let's just try that. I expect this will work with no change, but we just want to verify that. Looks fine. Ah, this encoder thing is nice. the main purpose of these encoders will be so that we can command the winchbot to move at a particular chord velocity, not a particular winch spool rotation rate. We're not relying on them to keep track of absolute position of the robot, because that would only work if the cord is not stretchy at all, which makes the whole system, I think, more prone to vibration and safety problems. So I'm actually happy that there's some compliance in the system, but that does mean that I'm using these more for motion feedback than for absolute positioning, just to clarify that. Absolute positioning is something I'm less concerned about. There are a few different strategies that will contribute to an absolute positioning solution. So here, port F, this is enabling the PWM generation peripheral. This should, I don't see how any of this would crash it. Let's just turn all this back on. I suspect the crash was probably in the interrupt code. Oh, am I not calculating the motor PWM period? That might have been the problem. I might have hit an assert in here. It's just calculating the number of clock cycles per motor PWM cycle. I'm running it at 25 kilohertz, which is, I think, what the motor driver H-bridge I'm using recommends. It's high enough to not be audible, but low enough to not put that much stress on the driver. Let's see if that works. Still fine. Cool. So at this point, we're almost expecting to get actual PWM output. We just haven't set the PWM rate. And I could just put in something here for debugging, but actually this next piece of code that I had disabled was supposed to be letting me set the PWM rate over UDP. So we might just try jumping right to here, because I think this is probably fine. So the watchdog thing is stubbed out. We're just assuming that it's always fine to run the motors. So in that case, we're ending up here, we turn on the PWM, and normally there would be a control loop here trying to keep the particular velocity that we want and adjust the motor PWM. But in this case, we're just setting the PWM based on what comes in over UDP, which is not good, but a good thing for testing. Let's see if this works. And oh, maybe not. Maybe this one's crashed. Could it be one of these? Oops. I think I might have to reset that. Oh yeah, that's back. So it was something in here. I don't think it would be this, because we're setting the pulse width using the same method up there. Is there something wrong in the PWM sync update? That's also the same code we call right up there. Okay, so what do we have so far? We've got this. We should be able to send this UDP packets that change the current motor command. Let's hide that camera for now. So we can send a packet that starts with this code, byte 4, and then that'll have these numbers in it: a velocity target, a maximum acceleration, and a force range. So byte 5 and then 4 32-bit integers. Or not 5, sorry. 4. So that should set the 4 integers we have. Oh. Can we have this not bind to the port? That'll let this coexist with the telemetry receiver. It was trying to bind, which would make it in charge of receiving packets, but I just want it to be transmitting right now. Oh, first argument is a rate. Is that not working out? Winch command. That's interesting. That's not what I expected. I expected this to give me a copy of this ABCD pattern in this packet. So maybe it's not processing these, or maybe I'm not transmitting them correctly. Let's do a quick TCP dump. Okay, these are the winch status packets coming back. How does this part work? Oops. That's what I wanted. Oh, is this sending it to the wrong robot? Is that the problem? I think I wrote this script when I was working on, when I was working on the flyer. Okay. Now I'm sending, I think, what I was expecting. That's what I wanted. Okay. So that is the motor command. So basically a copy of the last thing that the controller told the robot to do as kind of a loopback test. And so now we can see that the command counter is incrementing. It should be once per second because that's how often we're sending commands. And then the next counter, the tick counter, is incrementing 100 times a second. No, sorry, this is incrementing at the same rate as the packet's going out, which is why you're seeing it just count 1 per packet. So that's great. Then, yeah, then that's just those 4 words that we sent, the winch command, so that's a velocity target, acceleration, force, min and max. Then after that is sensors, which starts with the force sensor that we were just working on. So the force, yeah, the force measurement and the counter. So that's the force measurement. That's the force measurement counter. Then this is then we have the encoder. So that's the encoder position, velocity, acceleration. We have 2 more numbers, which are motor control, PWM and ramp velocity. So I think we're ignoring those right now. Yeah, right now those are being ignored. And so once we enable the next portion of this code, we're ignoring the stuff that we're going to be using as the motor PWM, and instead we're just going to be taking this number here, the velocity target that we can set over UDP, and sending that to the PWM generator as a test. But why was this crashing? Winch set motor enable. That's pretty harmless. Pulse width set and sync update. Why would either of those crash? Let's look at the code. PWM. That seems fine. Am I not calling this sync update function right? That seems fine. So this is intended to let you change multiple PWM units simultaneously. And so here I'm just using one for the positive side of the motor drive and one for the negative side. Okay, so what are my symptoms if I enable this again? Oh, good question from Geonag, I think, in chat, who asks, are the files uploaded to GitHub? They are. If you go to TucoFlyer is the GitHub organization, and then bot firmware is what we're working on. And so this one is based on this other repo, the TivaC repo, that basically is just a port of the TI dev kit. And this just adds a little bit of stuff on top of that to work with our robot sensors. Yeah, it seems to be crashing, so we're not getting any packets. Let's see if we get anything on the serial port. hard fault. All right, can we attach the debugger this time? So there are a couple things happening here. The hard fault is happening, and then we're getting stuck in a loop, and then the watchdog is resetting. So that's why we get kind of a spam of this stuff. So it's a little bit annoying to debug, so I might just try bisecting this first and just turn off. First I'm going to see which half of this it's in, and then I'll just repeat this until I know exactly where the problem is occurring. It seems maybe a little easier than wedging a debugger into this particular situation. It's also sometimes hard to program this when I'm also getting a spam of stuff out the serial port. So I think I might have to close the serial port and then try this. Or maybe reset it. This debugger seems to have a decent amount of trouble attaching when the device is in a watchdog reset loop. So far I've been kind of successful with just timing it so that I run the flash. So I apply power, then wait just the right amount of time, and then run the flash. I think I ran it too soon. I think that might have been the right amount of time. Robert's, of course, plugging Blackmagic probe. I have the Blackmagic probe here. I just using that would be nice. I just I'd have to modify this board to take out its onboard debugger first. Which is like, I mean, if I was committing to doing a bunch of debugging, then maybe I'd do that. It's just like, so far this firmware has been so simple that I haven't bothered. Usually it is not this annoying. Considered having it only enable the watchdog after the system's been running for a few seconds. Oh, yeah, I mean, Robert is suggesting another yak to shave. Why is this being so much more fiddly than it was last time I had this problem? also occasionally had problems with, well, I don't even know what to blame this particular problem on, but rebooting the Raspberry Pi seemed to fix it, which is super weird, but maybe we've gotten to that point again. Let's try that. Oh, Tuco looks so peaceful up there. Come back, little raspberry. That's a step in the right direction. That seemed to be an improvement. So, any telemetry? Yes. Okay, well, my GPIO was fine, so it was definitely one of these, but that's not much of a surprise. So, sync update or width set? Let's try just the sync update. Oh, I need to remount that. Right. Okay. Sync update. Period set. I mean, I've called these same functions up here. Is it just complaining maybe because maybe my value is just out of range? Is that the issue? Can I just take the lower 8 bits of this for testing? That didn't help. Pulse with the set or sync update. I don't see how that could fail. The parameters I'm sending it. using the wrong parameter for this one? No? Well, oops. Oh, did I? Maybe Control-Cing that was bad. I did that without even thinking. That might have contributed to the Linux USB stack being unhappy. No, that seemed better. Okay. Oh, still no telemetry. Oh, am I missing something about how these sync updates work? Let's try only commenting out the sync update. Did that again by habit. That's not happy either. Okay, maybe I need the on-chip debugger. Let's try that ICDI thing again. If that gives me too much trouble, I'll just modify the board so I can use a Blackmagic probe. So, man, the thing that doesn't add up though is that I'm going through these same steps up in the initialization. So I'm not sure what would be different down there. I mean, I'm in interrupt context. Other things have initialized. The parameter could be part of the problem, but let's just copy paste this down here without changing anything and then see if this works. And then the very next thing I want to change is to give it a non-zero value. It's a little slower than usual. Well, it looks like that crashed, and that's super weird to me. It's possible the crash is caused by something else. I mean, we don't really understand why it's crashing at this point because it's been inconvenient to debug at that depth. So maybe we just need to go a little deeper. So no telemetry. Yeah, are we still seeing a hard fault if we attach the serial port? Yeah. Well, let's try turning off the watchdog to see if that makes the little TI debug stub work any better. Definitely gonna make sure I remove that before checking this in. All right. Excuse me. So if I press reset, so now I get this Tuco flyer firmware starting, then it sticks in FH, and then nothing else. No reset, it just sticks there, which is what you want if you want to debug it. So this keyboard and I have not been getting along super well. So bot firmware. Oh, what if I press reset? Does that break into it? Yeah, I think GDB and this program, or the debug stub, are disagreeing on something. It's hard to tell what is actually relevant. No options there. Yeah, maybe I'm not going to fuss around with this debugger much more. I think either using the Blackmagic probe or just printf debugging might be easier. That would be really nice to know why I'm getting this hard fault. I'm also wondering if there's something special about the QEI interrupt. I don't know why there would be, though. just kind of hanging out. Not sure what event would cause this to break in successfully. Robert is telling me that the path that Robert is suggesting I go down is to write an interrupt handler that dumps out exception information, which is totally a thing I can do. The main issue is that I don't have, like, there's more stuff that I have to do to get reliable serial port in that context right now. Like, I don't think I can use the same UART printf that I'm using right now. So, like, yes, that would be an option. It's just not necessarily the most appealing option right now. Plus width set. Oh, you know what? I wonder if I'm out of stack space. That would be one explanation for this. Let's make sure we can reproduce the problem and then try turning up the stack space and see if that changes anything. Can we flash? Yes, we can flash. No telemetry. Okay. I also really don't like working with the watchdog timer off. Oh, that's fine. Bigger stack. I doubt this is the problem, but seemed worth testing. Yeah, not so much. Yeah, I think I'll just hook up the Blackmagic probe. So to do that, just requires some soldering. James is asking about whether does LMICDI actually support extended remote. I thought it did. I mean, we can check, but I thought I remembered it mentioning that in the README. Like, sure, we can check the documentation real quick. Was I imagining that this supports extended remote? Huh. Maybe it doesn't support extended remote. I guess we could try it without that. This is seeming similar. Yeah. All right, back to plan. Which plan is this? Is this A.5 or B.7? All right, so, oh, that was a bolt. So we can add a header here and take off all of these little resistors. I want the other soldering iron tip, actually. Drafty today. I'm going to use the solder blob approach to remove these tiny resistors. Removed. The main reason I was doing the development on the Raspberry Pi was also because of this adapter. It seemed to really not like macOS's USB stack. But I guess with the Blackmagic probe, I could move that back to this Mac if I wanted to. For just like quickly flashing these boards, it's pretty nice to have the onboard programmer. So I'll suspect I'll probably use that on most of these boards. But having at least one of these with the Blackmagic headers broken out for in-circuit debugging seems handy. I mean, so far the firmware has been simple enough that I've been able to mostly avoid it. Or the issues I've been worried about have been real-time stuff, like we need the scope for debugging anyway. get the black magic probe. I guess I can also supply power separately. All right, here's 5 volts of external power. That's better. Power. Alright, this delightful little creature. It's a black magic probe. Plug that into the Raspberry for now, because that's where I've been developing this so far. Alright. So, I think we want the fly wires and the serial lead. Ooh, is this the right pin out? No. Yeah. I think the fly wires are the way to do this. I had to check to see if these other pinouts might have matched, but nope. Oh, nice. Emily suggests, once it's set up, you could even make a cat detector / room map. Like, is there a cat in a sink Twitter, but automated? Yeah, yeah, definitely. I think between the thermal and the radar motion sensors, we'll have some good cat mapping technology. I need a pinout. There we go. So, 10 pins. They're so tiny. We have target voltage ref. This should go to one of my 3.3 volt pins. I might just enable target power on the black magic probe because I don't have a lot of 3.3 volt free right now. That's fine. How about ground? Got a bunch of grounds. 3, 5, and 7 are all grounds. There's 3. It's just bizarre to me that, like, well, so this isn't really useful as a JTAG header. This thing that I think they might have intended to use as a bunch of shorting jumpers that you can add, but you can't use it as a header because they didn't include ground or VCC or anything else useful, so it's a little bit annoying if you want to use something other than their onboard debug solution. And of course, this header would be convenient if it was for that processor, but it's for this processor. Okay, SWD, IO. SWD clock. Maybe reset. And serial port would be handy. And oh, this also has a VCC. So I think RX here goes to TX here and vice versa. I think that'll be my alternative debug interface for this board. Let's see if we can get this to come to life. Alright. So we have that open MoCo device is the Blackmagic probe. It should give us 2 serial ports. Cool, TTY HX711. One of those should be the device serial port. So we should be able to go access it with Minicom and see the same kind of debug stuff. I think that's ACM1. Maybe not. Maybe it was the other port. Oh, or maybe my board's turned off. I think it was the second port. Let's turn the board on. Yeah, serial port is operational. So now, over here, same debugger. Now we're just going to, instead of attaching to that little proxy thing, we should be able to attach to serial port. Why can't I use my own modem? Okay. I think I just need to log back in. Yeah. That's right, monitor SWDP scan. Alright, we need power first. Is this still coming through? Okay, something's unhappy. I cannot quit Minicom. So let's maybe reset the Blackmagic probe. This is a quick way of killing these apps that are connected to it. Maybe I don't have this hooked up right. So I have TMS connected to pin 2. TCK connected to pin 4. What is SWO? I have ground connected to pin 3. Let's just connect all these and then try JTAG in addition to SWD. TMS is 4, T clock, or 2, T clock is 4, and that's TDI. TDI is 8. TDO is 6. Is it 6 or is it 9? That one's definitely 9. That one's 6. Alright, I think I've got this crammed together. Let's see if we can detect JTAG. So Robert's suggesting that connect to S reset. We could try that too. Interesting. Well, I could turn off the watchdog again. If I could program it. I do have the reset pin connected to pin 10. It should be right. I mean, the thing that I was doing before to get this to work was basically just power cycling and then connecting at the right time. I wonder if the same approach would work here. So the board's off right now. So if it's off, when it's off, the scan fails right away. So no power, scan fails. That's not super helpful, is it? Are we getting reset pulses here? Alright, there's reset. That was a little reset blip, wasn't it? That doesn't seem right, does it? Huh. Maybe let's try not connecting reset, just in case. Is it possible I have these pins just totally connected to the wrong place? I mean, the connector is keyed. They're labeled. That seemed to be behaving as reset before. Yeah, if I plug that back on, it's driving reset low, which is weird. Oh. The voltage seems a little low too. That's like 2 volts. Where's that coming from? Yeah, that's the 3.3 volt logic level. So, do we have some contention? It's just super weird. Oh, whoa, what's going on here? Am I using the wrong half of this connector? Or... so this is probing the left side of the reset pin on the connector, and I'm seeing what looks like a 3.3 volt reset signal. And then if I probe the right side, that's the kind of low signal we were seeing before. Is it possible I've attached this to the on-chip debug interface instead of to the actual microcontroller? Without the Blackmagic probe, I'm getting 3 volts on both sides of that. Okay, which side of this is what we want? Let's pull up the schematic. It's this thing. I mean, that doesn't make sense, really. Like, if these sides were just swapped, then the serial port wouldn't have worked. Okay, well, what about one of these other pins, like maybe SWD clock? That's not a good level, is it? Let's take a closer look at what's actually wired to what in this board. So I'm going to try to trace this signal just to make sure things are actually as I expect them to be with the wiring. Yeah, so I should have a reset over here. That is going to the pin that I had connected to the debugger. This debugging makes me yawn. Okay, that's the target reset signal. That seems like 3.3 volts. Oh, so it looks like Joneg found a comment in the schematic that might suggest you can use that header on the side to debug the main processor with R40. Really? External debug. Oh, so this header is for the target? So, I mean, I'd rather not use this microcontroller than, like, tell this microcontroller nicely to tri-state the pins. That's interesting. Oh, I see. So that's for using that to program other boards, which is not what I want. Gotcha. Okay, so maybe I didn't actually have to remove these. Maybe it would have just nicely tri-stated those lines for me. That's fine. But yeah, no, that whole section of the document applies to a thing which I have just completely worked around, so I don't think that's important right now, but it's useful to know about. So So that is the target reset. Now I'm going to add the Blackmagic probe pin to that nut, if it'll fit. Yeah, so as soon as I add the Blackmagic probe there, it looks like it's pulling reset slightly down. Is that an artifact of the target power not being on? Ah, yeah, maybe that was it. Yeah, okay. So that's fine. Then let's take a look at the data next, or maybe the clock. Alright, that's the debug clock. Let's oh, wow, that's different. Huh. I'm gonna assume we only care about the first one. Finally, that's what we wanted. We have a debugger showing our hard fault loop. Yay. Okay, why was that not working before? Maybe the problem was I had that attached with the target power off, and then having the reset line pulled kind of half low like that was putting the chip into some kind of state that it was having trouble getting out of. And maybe just power cycling it after I solved that problem fixed it. So yeah, that's more like what I was expecting. Yay, hard fault. So, we have registers. We got a stack pointer. Do we have a backtrace? I don't think we would. Oh no, did trying to get a backtrace crash it? Okay, that's fine. Successfully canceled backtrace. Okay, so X. So we could also read the fault registers and figure out why the fault occurred. Usually the easiest thing is to just blop down the stack, and yeah. So where actually are we? Fault hard plus 10, D7E. Okay, so let's go look up which register we want to grab this data out of. I don't know whether this would be in the datasheet for this chip or in the Cortex M4 manual. It's probably in the Cortex M4 manual. I mean, I know it's in that manual. The question is, would they have copied it into this one? Probably not. Yeah, let's grab the Cortex M4 manual. Do I have that handy already? Technically this is an M4F, but these will be close enough. So my first intuition is that this would be in the interrupt controller docs, but maybe we'll just search for exception. Or fault, maybe. I've also written this code before, so I could probably pilfer it from somewhere. I've already written it. Like, specifically, where would I pilfer this from? I mean, I know I wrote something that does this pretty extensively at Siftio. Yeah. Oh, does that not actually do that yet? See, that's actually not quite what I was looking for. Well, might be easier to find it in their documentation than in my archaeology here. Fault status registers. Oh, is this it? Box fault. Oh. Maybe that's not what I want. HFSR. Oh, these come all the way from the ARM v7 reference manual. It looks like I want the hard fault status register. ARM v7. Oh, we want ARM v7M. Hard fault status register. There's not a lot of ways this can happen, huh? Dude. Oh, maybe I have. Maybe this was like a or like a memory protection fault or something else, and I have that handler set to a lower priority or something. I didn't change any of those, but maybe that's the default. Interesting. Let's see what's in this. Zero. We're in the hard fault handler, right? Debug fault. Is this... I don't know for sure if this is doing a 32-bit read or a 16-bit or a 8-bit reads. That's fine. Really? Well, there's non-zero values somewhere. That's the stack align bit. So far, the indications are that the hardware doesn't think that an exception is actually happening. I wonder if there's any way that I could spuriously end up here. I could also try just setting a breakpoint in the handler and see if I can end up here after a reset. The burnt popcorn smell has turned into a soy sauce smell, which is at least better. I still can't tell if that's just like something ambiently in the environment or like one of my neighbors. Hey, why was it trying to access D78 and why was it failing? That's interesting. Was it trying to do a software breakpoint there? Is there something different I have to do to set a hardware breakpoint specifically? I have no breakpoints. I'm used to it setting hardware breakpoints automatically. Well, I can do that. I can set the breakpoint on that particular address. And maybe reset. Huh. Let's trying to get what the reset command is. What else is going wrong here? Man, I feel like today's really going sideways with the debugging. I had all that success with a couple of drivers at first, and now I'm just failing to figure out why this processor is crashing. You only call it a crash when you don't know why it's happening. Well... Why? There we go. Power cycle. Was I using JTAG before? Does that matter? Okay, let's try doing this again in a really specific order without having any problems with browning out the target. It's also possible this might work better if I actually connected the target power reference, which I could do. I just need a spare 3.3 volts, which I guess I could steal from anywhere. Sure. Alright, VCC, pin 1. Alright, that's kind of far away, but it'll do. Alright, freshly booted Blackmagic probe, freshly booted target board. Remote debugging. So I want that failed a little faster. I'm getting a nice clock signal when I do the JTAG scan. Trying to actually get these waveforms. It's just the pads I'm actually poking are so little. Okay, I'm just going to poke the clock again because I want to measure its rate. Well. Wait, is that the clock? Oh no, that's TMS. That's the clock. I wonder if the clock is too fast. Can I slow down the clock? That's TCK. I'm expecting this to be a clock signal. That doesn't look very clocky. Oh, interesting. Yeah, I was looking at Gunag's suggestion that maybe it's something noise related, and I was touching reset when it worked before. Is it just me, or does it fail while the reset line is still low? Oh, that's the lag on the scope video. It's actually... Now it goes high. Well... It does fail really about the same time that goes back high, doesn't it? Okay, what if I don't attach reset? So that's the target reset without the board attached. Okay, and now I get a scan. Maybe I just don't want reset attached. That's weird. I mean, the main difference, I think, between this and last time I had reset not attached is that this time I have the reference voltage attached, but that's weird. Okay. I would have liked to get some more info about this before it hit this point. Now I want to reset it with this breakpoint still set. I could poke reset manually after pressing continue. Will that work? Of course you can't insert it. I wanted a hardware breakpoint. Is there a separate command for hardware breakpoints? I thought they were all automatic. So much bad advice on the internet. Oh man, I mean, I could also just tap out hard fault codes with Morse code. That's totally fine. I mean, I could also just do the work that it takes to make the serial port work in the hard fault handler, which I think mainly just means, like, writing... Oh, what is it that's keeping it from working anyway? Well, I think it's mostly because it's trying to communicate with another half that runs in an ISR. I could use the other version of the... There's like a compile time option that selects whether or not you have a ring buffer in between your UART printf and the actual serial port. And I think if I turned that off, then maybe I could use that within the hard fault. I think I might hit a different problem if I do that, though. Because I think I tried that before. I forget where that led. Can I flash code with this? I don't know if those packet errors are significant. I mean, I could also try doing this on a different host machine instead of the Raspberry Pi, but I really can't think of a reason why that would matter. Well, I might switch back to the onboard debugger just for programming this, and then try dealing without having a debugger for this particular problem. So if I wanted to get the onboard debugger back on, I just need to solder another header on and put some jumpers in. So maybe I should get that ready. Like, I would like to get the Blackmagic probe working on this board, but I think I also want to get my robot working. Oh, okay, so Peter says that one of the bugs I was hitting was a GDB bug that's been fixed in 8.0. Okay. We can try HBreak. Ah, cool. Let's see if we can get any more progress here. Okay, so board is powered. GDB. Communication. What GDB do I have on this computer? This is 7.10. This is also 7.10. Slightly different 7.10s. Do I need to reset this device again? Oops. That's different. Maybe I'm having a Raspberry Pi problem. Can I move this over to the Mac? Alright, let's try moving this. Actually want any of this. There. If there was anything I cared about in that repository or in that working copy, it's long gone. Oh. Certainly compiles faster on this machine. Oh. Why am I missing that definition? This is unrelated, but I might as well fix it. That should be in string. Maybe this is a problem with the version of newlib on here. The function obviously exists though. Oh, is there like a GNU source define or something I need to make? Let me check the header files. Oh, where's my compiler? I think it would just be in here. I know there's a way to get GCC to just give you a list of all the header files that it's using, but I'm not quite sure if I want to spend the time on that one. I can just grep. No, it's not in there. Yeah. POSIX visible or MISC visible. Interesting. Is that something that I can just set in my code? What's the intended usage of this? I mean, I see what they're getting at. This isn't, like, I don't actually have POSIX, but I do have some functions that these header files kind of owe me a definition for. Maybe this MISC is what I want. Might as well set GNU visible while I'm at it. Well, let's just change what I need right now. Let's not have this open also. Oh, is that if instead of an if def? Yeah. I need to find that to be 1 or something. This is just to get rid of a compiler warning. Not sure what I'm doing wrong there. These also might not be the version of these headers I'm using. Seems to be what I have installed. Is this what I'm missing? This reentrant library? Maybe this is like transparent reentrancy, whereas I want the version that is already reentrant. Not that it really matters, but it seemed nicer to use that version. And this is just where I was. And I should get that by setting misc visible. How can I test that? Oh, features. Maybe this is setting that based on something else automatically. Ah, or newlib extensions. Enabled by default. What? Why am I getting a warning if this is enabled by default? Default source, huh? Is that not already what I've got? Yeah. Is the compiler compiling this, maybe? Is my build system providing any of this? Okay, maybe I don't care that much about that, but it's slightly annoying. I guess it doesn't hurt to include my own definition for that. This restrict is, I think, a keyword that, oh, it's obsolete? Is that why you're bugging out my headers like this? Yeah, I could use that. Is this not reentrant either? Oh no, that's the... Yeah, I guess I could use this. This seems fine. It's a bit off topic to be changing my string code around just because of a compiler warning, but why not? Let's get all that junk off the screen. So I've been using this reentrant version of strtoc, which seems very similar to strcep. So you start out pointing string to a thing. Yeah. Oh, nice. So for empty fields, it returns an empty string. And it returns null only if the string was initially null. That's handy. And delimiter can be, yeah, any character. Cool. Yeah, let's change that. So... that's nicer. I hope this has strcep. That would be silly if it didn't. I think at this point I might just add my own implementation. Oh nice, I don't need this separate test to handle null cases anymore. This is just taking the argument, separating it with strcep, then checking to see if it parses successfully as a number. And if so, we proceed, otherwise it treats it as an invalid command. Yeah, now it's like, what is stirsup? So we don't have that in newlib. We should. Do we need BSD sources now? Oh, we're strict ANSI. Undef strict ANSI. I don't know if that applies, but I'm going to try this anyway because it's quick to try it. Oh, that did. I could go on and on, but no. Great. Does that fix the compile warnings? All of my warnings, at least. That one's in a library that I don't feel like patching. Okay, anyway, let's try the Blackmagic probe now. Fishbowl. All right, arm. Is that right? Is that the wrong serial port? Unlikely. Oh, the light on the Blackmagic probe is flashing. Almost flickering. Could this just be a USB problem? Try a shorter USB cable. And we know this computer has marginal USB the way I have it set up right now. Shorter USB cable. Oh, Piotr's asking what version of the firmware I have loaded. I don't know, actually. Could find that out. I guess it's probably DFU. Oh, right, the version was in that mon command. I mean, I can't really connect to it right now is the problem. I'll try unplugging everything from the other side of the board just to make sure there isn't some electrical problem. Oh, use the CU interface. Okay. Ah, that's better. Okay, that's the version. Firmware 1.6 RC0. I guess I could update to a release. Where would I find the releases? Okay, I think I've already got DFU util. Yeah. Let's just grab that whole command line there. So that's going to be the USB device IDs, and I assume beginning of the image or something like that, maybe the entry point. Do some DFUing. Oh, interesting. Apparently, according to Piotr, the Tiva chip has an issue where it resets the debug interface when the main system reset happens, which does seem really annoying for everyone to deal with. Alright, that seemed like a good flash. Yay. 1.6.1. Okay. So what else can we do? We can try to get a connection again. Address 0. I wonder where this target memory map comes from. Don't know whose message that is. Might just try loading the file. Yeah, just stop this. Stop all of this. Okay, this is compiled. That's the binary I want. Plug this back in. Then have we had any luck with JTAG scan, or has it all been SWD? Maybe it's all been SWD. That seems alright so far. That looks better. That stopped near but not at the beginning of the program. That's interesting. Well, we may have accidentally ended up in a usable state. It would only be coincidence if this firmware actually matches the image that I have loaded, because they're compiled in different machines, maybe with different versions of GCC. So I'm going to load this first. Or not. Are we still connected? So we are running... Okay, well... Anything gonna happen? No? I've got more blinking on the Blackmagic probe. Maybe that's serial port. Yeah. We are in a hard fault loop now. Okay, well, I'm out of ideas for the Blackmagic probe for now, so I think I might switch back to the other debug setup for the moment. Yeah, as Peter's pointing out, maybe this is just an issue where this particular chip needs a little bit of love on the Blackmagic probe support. Yeah, perhaps. That seems like a likely explanation for that part of what's going on. That might be a fun little project, because these seem like nice little chips. I could see using them in other projects, maybe. This aside and get some jumpers. That force sensor is working nicely though, at least as far as we can tell without any graphing. Definitely seems like it's working well enough for using as a kind of motor problem sensor. Alright, I need to solder a bunch of headers onto this. I think I have enough shorting jumpers to put all these back on. do. Delicious. Tasty, just like the Monopoly houses. Or the little Trivial Pursuit hexagons. I never really played that game, but I remember my parents playing it a couple times, and I always thought those pieces looked delicious. Don't remember ever dying by choking on one. Okay. Oh, I just noticed a comment from Preston in chat who says, "Greetings from Norway." Well, hello. Greetings from, I was about to say sunny California, although I think it's actually pretty overcast right now and a little bit cold. But the weather changes usually a couple times a day, so it's probably fine. Okay. I guess we'll go back to the Raspberry. Okay, let's plug it back into the Raspberry. Oh, yawns. The only change I want to pull over here is my little stir toke change. Let's make sure that works. Yay. Alright, let's try LM4 Flash again. Should make sure we can still program this board sometimes. Are we having more Raspberry Pi problems? Oh, there it is. I just plugged it into a different port. Maybe it wasn't plugged in all the way. James tells a story about the one time they played Trivial Pursuit and they rolled 20 threes in a row, or 20 plus threes in a row. With other people rolling values in between using the same dice, and they must have hit a glitch in the universe's random number generator. Yeah. Just like the glitch in this debugger. Yeah, maybe something that only enables the watchdog after a couple of seconds, or something like that. I mean, this all works fine until you get into a state where there's a bug that happens on startup, and then you have something like this happen, so you just have to not have that occur. It's as simple as not having any problems in your code. I think that worked. Okay, so I can program it, I just still have some timing that needs to occur. Okay, so now we're back to where we were a little while ago with this bug that is difficult, but we have a way of programming it again. So I could continue down the approach I was doing before, where I just kind of keep cutting down the problem until I reach the actual thing that's crashing. The other thing that's tempting to do is to try doing this outside of the QEI IRQ context, because the problem could be something I'm calling here, or the problem could be the time that I'm taking, or it could be that there's something special about the context I'm in when this interrupt is happening in the hardware, which seems a little more far-fetched. But so first, I'm just going to try deleting this. And I expect that by deleting this, I should get this firmware back into a state where it's mostly working again. And just to have some way of telling whether this is going to work, just so I can tell whether this works at all, I'm going to turn on that telemetry script again. Okay, so this will give us some output if the bot actually starts talking. Did that actually rebuild? Oh, right, I'm not actually editing the right version of this currently. Let's go back to editing the version of this that's on the Raspberry. Okay, so I just have those lines going away. And that's just based on what we've narrowed the problem down to be so far. I'm probably going to have to do a power dance to get this to go. Oh, maybe not. And we've got telemetry. Okay. So we have just bisected our problem again. Here's our sensors working. There's the encoder. There's the strain gauge. It is fun just to spin the encoder, though. That part certainly works. Aaron says, writing working C is as easy as not having any problems in your code, said some Hacker News user probably. Yeah, basically. I mean, programming is as simple as perfectly describing exactly what you want to do and doing so without any problems. So, you know, why isn't it just something that's always easy? All right, well, I think the next step is to take that code I just took out and to put it somewhere a little bit more harmless, like not in that interrupt handler that runs 100 times a second as soon as it boots, but maybe in a command handler. Oops. So let's take something like this and put it in the command handler. So I'm just putting that inside a little if, just so I remember this is temporary. I mean, not that it would be obvious, wouldn't be obvious, but. So this is basically the same thing that I wanted to do as my test, like way at the beginning of the stream. Ideally, I wanted to do this from the interrupt handler, but let's just, for the sake of testing, have this happen from a UDP packet handler callback. All right, let's flash this. All right, so we're working again. Now, can I crash it by sending it this UDP packet? Yeah, that one, 1904 is what I wanted. Looks like not. Interesting. Oh, I think I might know what's wrong. Is this just a race condition? Did I turn that interrupt on before enabling the PWM peripheral? I think that's what I did. That would have been really hard to figure out in a debugger, if that is indeed the problem. Okay, small steps. Let's just make sure this doesn't break anything. I wouldn't expect this to have any substantive change yet. Or, let's flash it. Alright, that's fine so far. Now let's take this code and move it again. That would explain the fault, because that would have had us writing to memory that was attached to a disabled peripheral, potentially. So, if that works, that's going to be a nice step. Let's try it out. Oh. That was a comment, not commented out code. And do we have telemetry? We have telemetry. I think that was the problem. So, this is getting called now with 0. So we should actually have the motor enable pin high now. We should have zeros coming out of the PWM engine, but then if we send it the right UDP packet, we should be able to turn on the PWM. So let's try that. First, maybe let's just hook some jumper wires up to all the signals we care about to have them all handy. So these will be 3 wires that will soon be going to the H-bridge driver, but right now I just want to scope them a little bit. Well, 4 if you count ground, which you always want to count ground. So these are PL1, PL2, and, no, sorry, PF1, 2, and 3. PF1, 2, 3, and ground. great. And PF1 is the enable output, which I guess I'll make yellow because yellow is exciting. And then we have two phases of control which go to the H bridge. They're kind of arbitrary, like swapping them just swaps the direction of the motor. So I'm going to just label them both blue right now. Okay. To the scope mobile. Alright, so yellow, I'm expecting this to be high. Yeah! Oh, that's good. Okay, cool. And then the other two should be low for now. Okay, let's get both of the PWM on the scope. The enable is not going to be interesting, or at least it shouldn't be interesting, so I'm going to leave that off for now, but I'll scope both of the PWMs. The enable will go low if, if I detect something wrong at runtime, like the computer stopped sending me packets, or the force sensor stopped responding, or something like that, the enable will go low. There will also be an emergency stop button locally, but that'll just cut the power to the whole system. And then it'll end up turning off the other robots via a more roundabout system where the robot that you killed the power to will stop responding with telemetry to the main controller, and then it'll notice that and stop all of its operations, and then each of the individual bots will stop whenever they, the controller will probably send an explicit stop command, but even if it didn't, all the winches would stop when they stop getting packets from the controller. All right, so those are my two PWM phases. I think we need the computer for this. So I have that kind of jury-rigged up to the velocity target. So I think that's the first number in this packet. Yeah, velocity target. So this field with all A's, I'm going to replace that with 0, just as a control experiment. So nothing changed. Now I'm going to try putting a 1 in there. So far I don't see anything. Let's try 80. I would expect to see something on the output at that point. That's 4. I did, build the firmware, right? Yeah. Okay, what about a negative number? Yeah, I don't see anything. I probably forgot an initialization step. Okay, so that's this PWM pulse width set. PWM sync update. Oh, that's right. I had this little debug kludge in there also, which I don't think I actually want. I think we should have still been seeing something, but let's just change that anyway. Yeah, it's just acting like the output's not enabled or something like that. Okay, so we need the GPIO pin type set, which is down here. GPIO pin configured. PF2 and PF3. Well, we could try comparing this against, like, the two other references that are useful for this really are the datasheet, which tells you kind of an initialization step by step in like very, very rough pseudocode. And then there's example code, which might end up telling you exactly what to do, but it doesn't cover every situation, of course. If I remember right, there was only like one example that used this PWM peripheral at all. Let's take a look at that. Yeah, so the only example that seems to use that at all is the example on how to do sleep modes. And they're using it, if I remember right, to blink an LED while the processor's hibernating. Disable output. It might be that I'm not doing the thing where I synchronize multiple PWM channels together correctly. I don't really need that feature. I mean, that makes it a little bit easier to switch directions without glitching, but I can do that even without that feature. So maybe let's try simplifying this a little bit. I think I want this to say no sync. And then I don't need these sync function calls. Okay, let's just see if that's any different. I don't know if I actually want to use that change, but it'll be instructive perhaps. I don't think that was related. Yeah, I'm gonna revert that. Not all of that. Just that. Well, let's at least commit this, because this is clearly a step in the right direction. Okay, maybe the data sheet. Pulse width modulator. Yeah, this is great. They have 2 of these modules that each contain 4 separate PWM generators. So maybe I'm missing something in the output control stage of this. I think these are the 2 pins I'm using. PF2 and 3, is that right? Yeah. So that's the same peripheral mapping that I have up here. Yeah, GPIO, PF2, motion control 0, PWM2, and then controller 0, PWM3. PWM generators must be configured before they're synchronized. There's a thing that I'm doing in the initialization where I thought I had to sync the initial value. I mean, this is after they're configured, so that's probably still fine. My thinking here was that I wanted to turn on the peripheral, then synchronize an initial value into it, and then map the peripheral to the output pins. I might be using this part wrong. I think I set it to locally synchronize, whereas actually maybe what I want is globally. Also, maybe I should try doing this without the synchronization feature first. Start the timers. Is that something I haven't done yet? Is that the missing step? Let's take a look at the PWM driver lib next. PWMO control, what writes to that? Need the hardware headers. Register offsets. Output enable. Oh. I guess that's a counter enable, is what that bit actually sets. And what sets that? Ah, PWM gen enable. I mean, I can reorder some of this stuff to match what it's telling me to do, but so far I haven't seen any really substantive differences. So I think this stuff can happen earlier. PWM gen enable is what actually turns on the counter, so I don't really have to worry about pulses coming out until that happens. Output state. Okay, let's try a simpler mode here. So no sync, maybe? And the other example I saw, that sleep mode example, they didn't even specify these other values, the debug stop and the... So I'm assuming the sync flag doesn't even matter when the sync is disabled, and there's probably a reasonable default for whether the counter starts or is running or not while the debugger is attached, and I don't really care at this point. So PWM 0 and 2. Period set. And just to make this a little easier to test, I'm going to set the pulse width to, I think, a 50% duty cycle right now. I'm just going to do that for both outputs, which is never something you'd actually do, but for testing. And let's just turn this off again. So I think everything else should be pretty much business as usual. And then during initialization, I'm hoping to see two 50% duty cycle square waves, but I don't know if I actually will. I kind of doubt it. I suspect the problem's elsewhere. Oh yeah. Chris is saying that the harder abstraction layers are often pretty bad, but you can use them anyway, or you could just go work around them. Yeah, I typically don't bother with the silicon vendor hardware abstraction layers. This is a little unusual that I'm using it this time. Part of it is that this one is actually not as bad as I'm used to them being, and part of it was that I kind of needed to, for the most part, to use their Ethernet code. But yeah, so far this is actually working out all right. They're, like, aside from some kind of stupidly worded licenses that they probably meant well by, but it's just, as long as I don't have to like modify that code, I just am compiling it into my project, it's fine. It will not make me vomit. Anyway, I think this loaded, but I still don't see square waves, so let's continue looking for problems elsewhere. Port F, pin 2 and 3. I know this mapping has got to be right, otherwise these pound defines wouldn't exist. Maybe now let's compare it against that example that we were looking at, because it's getting a little closer to that now. Sleep modes. I think that's the same configuration that I'm using at this point. Gen mode down, gen mode no sync. Yeah. I mean, I'm using different generator modules, but that's because I have the output connected to a different pin. So we have the output state true, out 0 bit. Yeah. Gen enable. We have gen period set, pulse width set. Maybe just to bracket this with something. Usually when I have something that doesn't work at all, it's nice to at least find some way of making it work, even if that's completely unrealistic, and then you try to find some intermediate steps. So maybe one thing I could do is setting these to be GPIO outputs and then just driving them in a loop here, and see if that at least shows up on the scope, just to make sure there isn't some other stupid problem with my wiring. I mean, I was just using this to look at the enable, which was high. could also take a break from this and come back to it with fresh eyes and try to find the problem later. We've made a lot of progress on this stream. Okay, well what happens if after all this I go back and I set up some GPIOs? Yeah, this GPIO pin type, GPIO output. And let's just toggle one of these maybe, PF2. Let's just generate our square wave in this interrupt handler. Is there a GPIO toggle, or do I have to keep track of the state here? If this works, I would expect, if this gives me the effect I'm expecting, I would expect to see a 100 hertz, no, 50 hertz square wave. It should toggle at 100 hertz. Is that it? Oh, 250 hertz, sorry. That's my tick rate, but yeah. Oh no, wait, what is that? That's every 4 milliseconds. Yeah, that's 250 hertz. Oh, well, so we know the output works. If I were to move this above the PWM initialization, that would check that we're successfully hooking the output up to the SSI peripheral instead of the PWM controller, or instead of the GPIO controller. Yeah, the PWM instead of the GPIO. SSI is not involved here. Ah, yeah, I should probably get a bite to eat soon. Well, that did give me a flat line. I don't know what's going on here. This is looking like it's mostly configured. I'm just getting zeros out of it. I could try inverting the output maybe, but I think I need to take a break from this. Feeling my stomach starting to complain. So yeah, still some debugging to do to figure out why this PWM isn't working, which seems really simple, but you know, there's all sorts of ways this stuff can fail. Once I get this working though, I should be really close to just being able to command the motor to do stuff. I can start throwing some really simple PID loops or even just a proportional loop in here to control the motor speed based on the sensor readings. Just trying to figure out what was going on in chat. Hard coding headers. So I was kind of intrigued by the idea of skipping as many network layers as I could for this. The reason I settled on using UDP instead of raw Ethernet frames was really just because it's so much easier to actually send them. For example, if I was writing this in Python on Windows, I looked into, well, how would I have to send these? And, well, the Windows API doesn't really give you a way to do that. So at that level, you end up using basically something like an I/O control that's part of WinPCAP. So then already receiving Ethernet frames, because I want to get telemetry back from here too. Now I'm signing up a user space app to process effectively all the packets that are coming in, which doesn't sound like what I want. I think I just want to use UDP at that point, you know. So anyway, I think that's pretty much the wrap-up point for this stream. Can have a moment of Tuco as I wrap things up here. Well, thanks for joining me for all this adventure. Had a little bit of success. I mean, actually a lot of success. I mean, the quadrature stuff worked pretty much right off the bat. That didn't require any fussing around. The force sensor, that worked pretty well. I mean, there was some kind of interrupt debugging that we needed to do to get it to not run twice when it should have been running once, but the actual thing where I break the 25-bit SPI transfer up into a 16-bit piece and a 9-bit piece, that worked just fine. So, all right, well, happy hacking, everyone. I'll see you on the other side.